All right, today we're going to be doing lesson 6.6, which is basically just complicated integrals. So we're going to do a lot of integrals that are just weird and kind of hard to do, and then we're going to do integrals that involve inverse trig functions. These first set of examples are rational functions, and when you look at them, like your first instinct may be to try to do a u sub, but for both of these first examples, the u sub doesn't work, because once you choose a u, you can't find the du in your problem. When you come to a problem like this, we are actually going to do polynomial long division. And I know it's been a while since you guys have done that. So you're going to do long division anytime the degree of the numerator is greater than or equal to the degree of the denominator. So like in example 1, you have x squared on the top and the bottom. So we're going to do long division. And I'll show you, once we've done the long division, you'll see why the long division is helpful in this case. I'm not giving myself any room. So you're going to put whatever's on the denominator on the outside of your division bar, and then you're going to compare what do you multiply x by to get, x squared by to get x squared, and that's a 1, so you put a 1 on top, and then you multiply the x squared plus 2 by 1, you get x squared plus 2, and then you're going to subtract these. So this whole thing is being subtracted. So then you just end up with a negative 4x. And then at this point, you can't multiply anything by x squared to get negative 4x squared. So we are done with the long division. And our answer would be 1 minus 4x divided by x squared plus 2. That negative 4x is considered the remainder. So it goes on. It's still divided by the x squared plus 2. So the reason that is helpful for us is that now I can change my integral into 1 minus 4x over x squared plus 2 dx. Which is also nice for us because now that I have these two things that are being subtracted, I'm going to split this integral up. So I'm going to split up into 1 dx minus the integral of 4x over x squared plus 2 dx. Now that first integral is super easy for us to do. The second integral is going to require us to do a u sub. So I'll go ahead and put that right here. So u is going to equal x squared plus 2, which means the du is 2x dx. In order to get that 2x dx, I'm going to take this 4 and I'm going to split it up. I'm just going to make it 2 and then put a 2 in front. So I can see that 2x dx showing up really clearly in my integral. And now I'm ready to actually integrate. So the first integral, 1 dx, is just going to turn into an x minus 2 times the integral of 2 over u du. Sorry, there shouldn't be a 2 on top right there. That should just be a 1 over u. That 2 became the du. So then this turns into x minus 2 natural log of the absolute value of u plus c, and then I'm going to go ahead and put my x's back in. So I get x minus 2 natural log of x squared plus 2, absolute values, plus c. Don't forget your plus c on this one because you don't have bounds, so you're going to have a plus c. All right, that was the first type of kind of weird integration. Just as a note, long division is not a super, super common thing that you're going to see. So I wouldn't stress too much about it. I would learn how to do it, but I wouldn't kill yourself learning how to do long division of polynomials. Okay, the next one is also going to be a u sub. We're going to start with a u sub, but it's going to look a little bit weird. So what we're basically going to do with our u sub is we are going to eliminate all of our square roots. So we're going to say let's let u equal just the square root of x. So then my du is equal to 1/2 x to the negative 1/2 dx. Okay, now this du doesn't really show up anywhere in our problem. right? It's kind of a weird thing to see. So what we're going to do is we're going to do something different. We're going to solve for dx. So we're going to do some rearranging right here. We're going to say that 2 square root of x du is equal to dx. Okay, that's just some algebra. And then we're going to convert this side right here into u's. So we know that the square root of x is u. So 2u du is equal to dx. Okay. This is a very weird u sub, but let's see what it looks like once we convert our integral into u's. So we have the integral. The fraction will be easy. It's just going to be 1 over u minus 1. And then we have this dx piece. And we just said that dx equals 2u du. So I'm going to have this, instead of dx, I have 2u du. So essentially what I have is I have the integral of 2u over u minus 1 du. Now, if you'll notice, the numerator has the same degree as the denominator, so we're going to do some lovely long division. So we have, I'll do this in blue right here. We have u minus 1 divided by 2u. So I'm going to multiply it by 2, and I get 2u minus 2, which I'm going to subtract. So I end up with the remainder of 2. So my answer would be 2 plus 2 over u minus 1. And now I'm ready to rewrite my integral. It's going to be a lot simpler. It's going to be 2 plus 2 over u minus 1 du. So I'm just taking the answer to my long division problem and replacing the integrand with that. And then I'm actually going to split this integral up so that I can just deal with it as 2 separate things. Mostly because my second one is going to require a u sub, but I'm already in u, so I'm going to do I'll just do a double u sub. So we'll say w equals u minus 1, which means that dw is equal to 1 du. So I'm just going to bring this 2 out front so I can really easily see that 1 du showing up inside. So then I end up with 2 du plus 2 times the integral of 1 over w dw. And now I can integrate. So I have 2u plus 2 natural log of the absolute value of w plus c. And I've got to start changing everything back into x's. So I need to go back to my original u sub. The u's were square root of x, so I have 2 square root of x. And then I'm going to change this w just into a u. So my w's were u minus 1. And then I'll change that u back into x's. Okay, and this is my final answer. That one is a really complicated one. It requires a lot of creativity and just kind of creative thinking as you work through it. All right. So those are probably, these ones we just barely did. These are less important than the ones we're about to do. So if you can only handle learning one of them, don't choose the ones we just did. Choose the ones we're about to do. We're going to talk about how do we integrate inverse, sine, cosine, and tangent. So if you remember our derivatives of sine and tangent, you're going to see them right here. So the derivative of sine and the derivative of tangent. This is going to be important for you. First of all, those should still be memorized for you. Whenever you see something that looks like either of these derivatives, you need to be thinking, okay, these are related to the arc sine and the arc tangent. So let's go ahead and do a practice differentiating an arc sine so you can remember what it looks like. So we're going to do this one-month example right here. So if y equals the arc sine of x squared, and we want to differentiate it, so we're trying to find the derivative, y primed would be 1 over the square root of 1 minus whatever thing is inside of the arctangent. So x over 2 squared. And then you would need to multiply by the derivative of what's inside of the arctangent, which is 1/2. Maybe like a nicer way to write that would be 1/2 square root of 1 minus x squared over 4. Now, the next step that I'm going to show you, I wouldn't do if I was differentiating, but it does kind of show you where we're going to, how it's going to be related to its integral rules. I'm going to take this 2 and I'm going to shove it inside of the square root. When that 2 goes inside of the square root, it becomes a 4 because the square root of 4 is 2. So I end up with 4 times 1 minus x squared over 4, which is equal to 1 over the square root of 4 minus x squared. So when you see something like this, our answer, we know that if we work backwards and do it correctly, we're going to be able to end up with an arc sine as part of our integral. This is something that I would memorize. I hate adding things to your guys' memorizing list. But if I were you, I would memorize this box. It's just going to be the easiest way to integrate arc sines and arctangents. Okay, I'm going to try to zoom out so we can see that box at the same time that we're doing number 3. So when we're looking at number 3, we are integrating 1 over the square root of 4 minus x squared. You'll notice that we already know what the integral of that is because it's the same as this problem we just did right here. So we're going to work through it using this method, and we should get arc sine of x over 2 if we do it correctly. So first of all, we need to recognize that we're dealing with something that's going to integrate into an arc sine because we have a constant minus an x squared. So we're dealing with an arc sine. So if we're dealing with an arc sine, what we want to do is we want to identify what the a, the u, and the u primed are. So we have a, we have u, we have u primed. So the a is the constant that's being squared. So in this case, our constant is 4, so our a would be 2. It's the square root of that. Our u is the function part that's being squared. So in this case, we're squaring an x. And then my u primed is just the derivative of u, which would be 1 dx. So just like anytime you have u's in your problem, you want to make sure u primed does show up somewhere in your integrand. And in this case, it does. If not, we have to modify to force it to show up. Once we have our a, u, and u primed, we're just going to plug it into this formula right here. The arc sine of u over a plus c. So my integral is the arc sine of u over a plus c. Okay, let's go ahead and do another one. Hopefully you can kind of toggle back and forth between the formulas at the top and then these problems. So number 4, we're dealing with a function piece squared plus a constant squared. There's no square roots here. So this is going to be an arctangent problem. Okay, so we're going to find our a, our u, and our u primed. I'll do that. I'm going to do it right here. So our a is going to be, again, the constant that's being squared. Our u is the function piece that is being squared, so it'd be 2x. And so that means our u primed, or our du, I'll write it as du, because that's kind of what we've been doing. Our du is going to be 2 dx. So before we go ahead and jump to our formula, we want to make sure that 2 dx shows up somewhere in our integral, and it doesn't. So I'm going to put a 2 in front of the dx, which means I've got to throw a 1/2 in front. So then when I integrate this, I'm going to have the 1/2, and then my formula for arctangent is 1 over a times the arctangent, of u over a plus c. All right. Okay, let's do another one. Notice that in number 5, I am now dealing with a definite integral, which means that I have bounds. So I'm going to start by just finding the antiderivative. So find the u and the a and the du. So I'm going to do this up here. We're going to need more space for this one. So my a, my u, and my du. The a is the constant that's being squared. This would be the square root of 3. My u would be 2x, which means, and my du would be 2 dx. So I'm going to go ahead and split up this 8 right here so I can see the 2 dx and throw the 4 in front. So the 4 times the 2 would create the 8, but I'm splitting them up. Okay, now I am ready to integrate this. So I have 4 times 1 over a times the arctangent of u over a. And I'm integrating from 0 to 1/2. So then I've got to plug in my bounds. So I have the 4 root 3. Just going to kind of throw that in front. And then I need to find the arctangent of 1 over root 3 minus the arctangent of 0. And now we're going to test to make sure that we remember how to find the arctangent of things. So that 4 over root 3 is just going to stay constant in the front. So I need to figure out where on my unit circle does the arctangent equal 1 over root 3. And that would be places that where the sine is 1/2 and the cosine is root 3 over 2. So that would be pi over 6. And then the arctangent is 0 wherever the sine is 0. So that would be at 0. So then this would be my final answer. If you wanted to rewrite it as 4 pi over 6 root 3, you could. But that's going to be my final answer. Okay. All right, let's do some more. One thing to be cautious of is that this method of doing arcsines and arctangents is great, but you always want to make sure that you're only doing it when it actually applies. So for example, in number 6, we don't actually need to use anything with arcsines or arctangents because we have an 8x on the top. If you have an x on the top of your fraction, you're likely not going to be able to use inverse sine and inverse tangent. Number 6 is even easier. It's just a basic u sub that we're hopefully getting really, really good at. It'd be 3 plus 4x squared. And then our du would be 8x dx. So I can see my du showing up right here in my integral, which means I can just convert this whole thing to 1 over u du. So when I integrate it, I get the natural log of the absolute value of u plus c. Convert back to x is natural log of 3 plus 4x squared plus c. And I'm done. Okay. Again, with 7, we might look at the denominator of that and think, oh, that looks like an arctangent. I'm going to do an arctangent problem. But if you look at the numerator of number 7, you have an x squared on the top. So the first thing we need to do here is we need to do polynomial long division, just like we did in the first couple examples. I'm going to do that in blue over here on the right. So I have 3 plus 4x squared divided by 8x squared. So I'm going to multiply that binomial by 2. So I get 8x squared plus 6. I'm going to subtract all of that, and I get negative 6. So I end up with 2 minus 6 over 3 plus 4x squared. I'm going to go ahead and rewrite my integral now. Now it's just 2 dx minus the integral of 6 over 3 plus 4x squared dx. And now this integral, have we done this one yet? We have not. Okay. This first integral is easy. The second one, now that one is going to be an arctangent problem. So let's go ahead and get our u's, a's, and u primes out to figure out what this one's going to turn into. So our a is going to be the square root of 3. Our u is just going to be 2. Our u is going to be x. Wait a second, I've dropped something. This should be, I'm sorry guys. this should be 4x squared. I don't know why I forgot that 4. So my u is going to be 2x, which means my u primed is 2 dx. So I'm going to split this 6 up to a 2 on the inside, a 3 on the outside, and now I am ready to integrate. Okay, now we're ready to go ahead and find and actually integrate. So the first integral just turns into 2x, and then we have minus 3. Oh my gosh, I have another typo, guys. I'm so sorry. This a is the square root of 3. So I have 3 times 1 over a times the arctangent of u over a. So 2x over square root of 3 plus c. That one's kind of a beast of a problem. All right, let's go ahead and do this very last one. So this last one, we've got 2 things that are being added together on the numerator. This is a pretty classic way to start the problem. If you have a numerator that's being added together, just go ahead and split it up. So it's we're gonna make it x over the square root of 4 minus x squared dx, and then plus 4 over the square root of 4 minus x squared dx. And then we're going to treat both of those integrals as 2 separate things, and we're going to integrate them both separately. I'm going to do this first integral all in blue and the next one all in green so you can easily see which is which. This first integral is just going to require a basic u sub. 4 minus x squared, where du would be negative 2x squared dx. So I'm going to throw a negative 2 in my integral. So I'm going to throw a negative 1/2 in front of my integral. And this turns into negative 1/2 times the integral of 1 over u du. 1 over u, 1 over square root of u. Sorry, guys. I'm going to go ahead and rewrite that as u to the negative 1/2. And now I'm ready to integrate. So it'd be u to the 3/2 divided by 3/2. I'll go to make that look a little bit better. I'd end up with negative 1/3 u to the 3/2. Did you guys all catch my mistake right here when I actually integrated? I just caught it. When I add 1 to negative 1/2, it becomes a positive 1/2. So I end up with this, which is just going to be negative u to the 1/2. So my first integral just turns into negative square root of 4 minus x squared. Now my next integral we're going to need to use one of our arcsine or arctangents for. Notice that we have a square root, so it is going to be an arcsine. So we'll find our a, our u, and our du. Our a is the square root of the constant, so it's 2. Our u is the square root of the function piece, so it's x. And then our du would be 1 dx. So I'm just going to take this 4 that's inside of my integral and just put it in front. So this integral is going to turn into 4 times the arcsine of u over a, x over 2. So we've integrated both of these separately. Now we need to put them together as a final answer. So my final answer would be negative square root of 4 minus x squared plus 4 arcsine of x over 2 plus c. That one's also a fairly typical problem because if you can remember to split up that integral at the beginning, like we did, then one problem can test your knowledge of u subs and your knowledge of arcsines at the same time. All right, example number 9. So when you first look at this, it tells us to complete the square, and we're going to do that in a second. But let's talk about why we have to complete the square. If you look at this, you can't do any long division because the numerator isn't bigger than the denominator. You can't do like an arcsine or an arctangent because you don't have like a nice, neat, like one thing squared plus or minus another thing squared. And you can't do a u sub. So we are going to complete the square on this. Now, I do not know how you guys have learned to complete the square, so I'm going to walk you through how I would complete the square on this, which might look different than the way that you guys do it. Okay, so when I'm completing the square, I know I'm going to have a binomial squared and then plus or minus something at the end. The first piece is always going to be x. So the piece that's squared has to match up with my 4x right here. So I'm going to take half of the 4 and put it in here. So I have an x plus 2 squared. That's going to be the first piece of my binomial. Now I'm going to think about if I were to actually square that, I would end up with an x squared plus 4x plus 4. That's what that binomial would square out to be. In order to make this match what I started with, I need 4 more. So I would need to add 4 here to match up with what I started. So this is going to be a plus 4. Okay, so I recognize that might be a different way of completing the square than you're used to, but complete the square however you want. You should end up with x plus 2 squared plus 4. So I can rewrite this over here as 1 over x plus 2 squared plus 4. And now we can do a u sub. Well, we can do an inverse tangent, find the u, find the a, find the u primed. So if I let my a be the constant squared, it would be 2. My u would be whatever function is being squared, so x plus 2. And then my du would just be 1 dx. And I do have a 1 dx right there in the problem. So I can just go ahead and rewrite this as my final answer. It'd be 1 over a times the arctangent. Whoops, I need the t in there. Of u over a plus c. So completing that square allowed us to put that polynomial in a form that we could use the arc sine or the arctangent for. All right. So these last two that we're going to do, this is the end, we have to just use creative thinking for. So for number 10, I'm going to start by splitting this up into 2 separate integrals. The integral of 3 over 1 minus the square root of 1 minus x squared minus x over the square root of 1 minus x squared. And they both have a dx there. And then I'm going to evaluate both of them separately. So I'm going to bring the 3 in. Actually, I'll do these in different colors again. I like that. This first one, I'm going to bring the 3 in front and end up with just 1 over the square root of 1 minus x squared dx. Now this integral, we hopefully can recognize that is the antiderivative. That is the derivative of the arc sine. So this is just going to turn into 3 arc sine of x. And if you were to do the u's and the a's and the u primes, you would end up with 3 arc sine of x. This second integral, we're going to need to do a u sub for. So u is 1 minus x squared. Du is negative 2x dx. So I need this to be a negative 2x, which means I need to put a negative 1/2 in front. So then I'm going to end up with 1/2 times the integral of u to the negative 1/2 dx. Then hopefully I'll do this addition right this time. I'll get u to the positive 1/2 divided by 1/2. And the 1/2 will cancel out, and I'll just end up with u to the 1/2, which is the square root of 1 minus x squared. Then I'm going to go ahead and put everything together. So I have my first integral, which was 3 arc sine of x, plus my second integral, square root of 1 minus x squared, and then, of course, plus the lovely c at the end. That would be one that hopefully you'll be able to kind of piece that one together on your own after having gone through the rest of the examples. All right, example 11. This one is really just a weird one. You just have to get creative when you're thinking about this one. We have 1 over e to the x plus 1. You can't do a u sub. You can't do any arc sines or arctangents. You can't do any long division. So we're just going to try to get creative with it. So what I'm going to do with this is I'm just going to do some algebra to change this. I'm going to add e to the x to the top, and I'm going to subtract e to the x, which feels like a dumb thing to do, I know. But I'll show you why that's a little bit useful. So if we just add and subtract e to the x to the top, we haven't changed anything algebraically. But what we can then do is we can make this, we can write the top as 1 plus e to the x, we're going to kind of group that together, minus e to the x over e to the x plus 1 dx. And then I'm actually going to split this up into two separate integrals. I'm going to have the first one, 1 plus e to the x over e to the x plus 1. So just that first parentheses over the denominator. And then minus the integral of e to the x over e to the x plus 1 dx. And then we're going to treat both of them as separate integrals. So this first integral is really nice. It's just going to be, you'll notice the top and the bottom are the same. So it's just the integral of 1, which is just going to be x. So the first one, nice and easy. The next one we're going to do a u sub for, just a regular old u sub. So u is going to equal e to the x plus 1, which means our du is e to the x dx. So this integral turns into 1 over u du, which is going to be the natural log of the u, which is e to the x plus 1. And we have the plus c. So this whole thing right here is going to be the answer. And this is just one where you have to just start trying to get creative. So try everything you know, and if it still doesn't work, try doing weird algebra to it.